If the force of gravity were just a fraction stronger, the universe would have collapsed into a fireball eons ago. If it were weaker, stars would never have ignited to create life. Is it possible that the entire cosmos was precision engineered just so you could exist to witness it? This question does not arise from idle speculation, but from the precise measurements and theoretical calculations of modern physics, which reveal that the fundamental parameters governing our reality are balanced on a knife's edge. A universe slightly different in any one of several key respects would be incapable of producing the stable atoms, the long-lived stars, or the complex chemistry necessary for life to emerge and for consciousness to eventually ask why the universe is the way it is. The implications are staggering, suggesting that our existence may not be a random accident in an indifferent cosmos, but the result of conditions so finely calibrated that they demand an explanation. This apparent fine-tuning of the universe for life raises one of the most profound questions in science and philosophy. Is the cosmos inherently structured to give rise to observers like us, or are we simply the beneficiaries of an extraordinary statistical fluke in a much larger reality? The Anthropic Principle offers a framework for thinking about this puzzle. But to grasp its full weight, we must first understand what these fundamental constants are and how they shape every aspect of existence from the smallest particles to the largest structures in the cosmos. Only then we can appreciate why even small deviations would transform our universe into something unrecognizable and inhospitable to life, and why the narrow window we inhabit feels less like chance and more like a cosmic invitation to exist. At the heart of everything lies a set of numbers that physicists have measured with extraordinary care, yet cannot derive from any deeper principle with our current theories. These are the fundamental constants. The gravitational constant g that set the strength of attraction between masses, the fine structure constant alpha that governs electromagnetism and the bonds holding atoms together, the coupling strengths of the strong and weak nuclear forces, the masses of quarks and leptons, and the cosmological constant that derives the universe's accelerated expansion. Together, they form the invisible rulebook of reality. In the hot, dense plasma of the first moments after the Big Bang, these constants determined how particles interacted as the cosmos cooled, how quarks formed into protons and neutrons, how nuclei formed, and how the first stars eventually ignited. Their values were not chosen by us. They were simply the ones that allowed the universe to evolve from a featureless fireball into a place with galaxies, chemistry, and minds. Consider the strong nuclear force, the interaction that binds quarks inside protons and neutrons and holds atomic nuclei together against the electromagnetic repulsion of protons. Calculations show that if its strength were increased by even 1%, the consequences would be catastrophic for any prospect of life. The increased binding would make a stable diproton possible, allowing two protons to stick together without a neutron. In the early universe, this would have triggered runaway fusion during Big Bang nucleosynthesis, converting almost all available hydrogen into helium and heavier elements almost immediately. The result would be a cosmos starved of hydrogen, the simplest and most abundant element, the fuel for long-lived stars and the key ingredient in water and organic molecules. Stars, if they formed at all, would burn through their fuel in cosmic instants rather than shining steadily for billions of years. There would be no slow, steady stellar lifetimes for planets to form and cool, no time for chemistry to build complexity, and no abundant hydrogen to serve as the raw material for life. The universe would flare brilliantly and then fade into a darkness without the ingredients or the timescales needed for anything resembling biology. Shift the strong force in the opposite direction by a comparable amount and a different sterility emerges. Nuclei would struggle to bind at all. The deuteron, the simplest compound nucleus, might not exist as a stable state, and heavier elements would never assemble. The periodic table would shrink to hydrogen alone, a universe of isolated protons drifting in a thin gas that could never clump into stars or planets. Without carbon, oxygen, nitrogen, or the metals that form rocky worlds, chemistry would remain primitive, limited to the simplest interactions. There would be no molecules capable of storing information, no self-replicating systems, no evolutions, and no observers. Between these two extremes, our universe sits in a narrow band where the strong force permits a rich variety of stable nuclei, the forging of heavy elements in stellar cores, and the long-lived stars whose light and heat give life time to arise. This is the cosmic tightrope we walk, a balance so delicate that it invites us to ask whether the laws of physics were written with life in mind. The beauty of our functional cosmos, with its galaxies, stars, planets, and the intricate chemistry that makes biology possible, stands in stark contrast to the barren outcomes that seem far more probable if the constants were selected at random from a wide range of possibilities. The probability of hitting even one of these narrow windows by chance appears vanishingly small. The probability of hitting all of them simultaneously strains credulity. Yet, here we are, in a universe old enough for multiple generations of stars to have lived and died, enriched with the heavy elements needed for planets, and governed by forces that permit both stability and change. The Anthropic Principle begins with this observation and asks what it means for our understanding of reality. The same precision appears when we examine electromagnetism. The fine structure constant, approximately 1/137, sets the strength of the electromagnetic interaction. It determines the size of atoms, the energy level of electrons, the strength of chemical bonds, and the way light interacts with matter. If this constant were even a few percentage larger, atoms would become unstable, electrons might be pulled too tightly into nuclei, or the quantum rules governing orbitals would shift, preventing the formation of stable molecules. Chemistry would collapse, and with it the possibility of the complex, information-bearing molecules that life requires. If the constant were smaller, the electromagnetic force would be too feeble to hold atoms together against thermal motions or to enable the sharing and transfer of electrons that create the bonds of chemistry. Solids and liquids might not form in the familiar way, and the rich periodic table we rely on would not exist. Our universe occupies the narrow range where electromagnetism permits both stable atoms and the intricate molecular architecture of biology. Gravity, though vastly weaker than the other forces, is tuned with equal care on cosmic scales. Its strength relative to electromagnetism is roughly 1 part in 10 to the 40th, a hierarchy that allows matter to clump into galaxies and stars without the universe recollapsing almost immediately after the Big Bang. If gravity were appreciably stronger, the expansion of the early universe would have been reversed before stars could form or planets could cool. The cosmic clock would have run out long before life had time to evolve. If gravity were weaker, density perturbations in the primordial gas would have never grown into bound structures. The universe would have remained a thin, featureless haze expanding forever without the lights in the sky or the localized environments where chemistry could concentrate and evolve into life. The fact that gravity is strong enough to build galaxies and stars, yet weak enough to give the universe more than 13 billion years of expansion, is another thread in the web of fine-tuning. The weak nuclear force responsible for beta decay and the initiation of fusion in stars completes the set of interactions whose strengths appear delicately balanced. In stellar cores, the weak force allows protons to convert into neutrons, enabling the fusion chain that powers stars and produces the light and heat that sustain planetary environments. If this force were significantly stronger or weaker, the rates of these reactions would shift. Stars might burn through their fuel in mere millions of years instead of billions, leaving insufficient time for biological evolution on orbiting worlds. Or the fusion reactions might fail to ignite efficiently, leaving the universe dark and cold. In the first minutes after the Big Bang, the weak force helped fix the ratio of neutrons and protons, which in turn determined the abundances of the lightest elements. A different strength could have produced a helium-dominated universe with little hydrogen left for water, or for the long-lived stars that provide stable conditions over cosmic timescales. These examples only begin to map the extent of the fine-tuning. The mass difference between the neutron and the proton is a mere 0.14%. Yet, this tiny gap allows neutrons to decay outside nuclei while protons remain stable inside atoms. Reverse the ordering and the universe would lack stable hydrogen, eliminating the most basic building block of chemistry. The Higgs vacuum expectation value sets the masses of many fundamental particles. Shift in its value would alter the stability of matter itself. Even the initial conditions of the Big Bang, including its remarkable uniformity and the precise amplitude of its density fluctuations, represent additional tunings that allowed structure to emerge rather than a featureless soup or a chaotic scramble. Each of these parameters could in principle have taken a wide range of values, yet all of them sit in the narrow bands that permits atoms, stars, planets, and life. Perhaps the most dramatic illustration comes from the cosmological constant, the energy density of empty space that is currently accelerating the universe's expansion. Quantum field theory predicts a vacuum energy vastly larger than what we observe, by a factor of roughly 10 to the 120th. If this constant were only slightly larger than its measured value, the repulsive effect would have dominated early enough to prevent galaxies and stars from ever forming. The universe would have expanded too rapidly for gravity to gather matter into bound structures, leaving a dilute, lifeless expanse. If the constant had the opposite sign or a different magnitude that caused recollapse, the cosmos would have ended in a big crunch long before life could arise. That we inhabit a universe with the cosmological constant is tiny enough to allow structure yet large enough to eventually dominate is a fine-tuning of almost incomprehensible precision, one that has been called the most severe fine-tuning problems in all of physics. Faced with the convergence of apparent coincidences, physicists and philosophers have developed several ways of thinking about why we observe a life-permitting universe. The weak anthropic principle observes that we could only find ourselves in a universe whose parameters allow observers to exist. Any universe where the constants fell outside the life-permitting ranges would contain no one to notice the problem. Our measurements are therefore subject to a selection effect. We necessarily observe conditions compatible with our own existence. This principle is logically sound and cautions us against assuming that our universe is typical without accounting for the fact that we can only exist in certain kind of places. It explains why we see what we see without invoking design. Yet it leaves unanswered the deeper question of why such life-permitting conditions exist among the vast space of possible realities. The strong anthropic principle goes further, suggesting that the universe must have properties that permit the existence of observers at some stage. This version borders on the teleological, implying that the emergence of life and mind is not accidental but in some sense built into the fabric of reality. It has inspired speculations that consciousness may play a more fundamental role than we usually assume, perhaps even participating in the actualization of physical laws through quantum measurement. While these ideas remain speculative and difficult to test, they highlight how the anthropic principle blurs the boundary between objective physics and the subjective experience of observers who can reflect on the laws that can make their own existence possible. To explain the fine-tuning without design or strong teleology, many physicists invoke a multiverse. If our universe is one of a vast or infinite ensemble of universes, each with its own set of physical constants, then the apparent tuning becomes statistically expected. Processes such as eternal inflation or the enormous landscape of possible vacuum states in string theory could generate universes with different parameters. In the overwhelming majority of these universes, the constant would lie outside the narrow windows required for atoms, stars, or chemistry. Those universes would be sterile, short-lived, or structurally barren. But in the rare ones where all the dials align, complexity can emerge and observers can arise to ask why the universe seems made for them. We find ourselves in such a universe not because of extraordinary luck or intent, but because it is the only kind of place where beings like us can exist to pose the question. The multiverse does transform the fine-tuning puzzle from an improbable coincidence into a natural consequence of a much larger reality. Yet, the multiverse hypothesis carries its own difficulties. Other universes, if they exist, are generally unobservable, separated by inflating space or different physical laws that prevent any interaction or direct test. This raises concerns that the idea functions more as a philosophical framework than as a conventional scientific theory with falsifiable predictions. There is also the measure problem. In an infinite multiverse, how do we define what is typical or probable when there may be infinitely many universes of every kind? Without a rigorous way to count or compare outcomes, it becomes difficult to claim that life-permitting universes are rare or that our observations are expected. The multiverse does not eliminate the need for explanation. It shifts the question to why the larger reality permits such a diverse landscape of constants in the first place. Alternative approaches seek to resolve the fine-tuning without invoking multiple universes. Some physicists hope that a more complete theory of quantum gravity or a deeper formulation of string theory will reveal that the constants are not free parameters at all but are fixed by mathematical necessity. In this view, the apparent tuning would be an illusion created by our incomplete understanding. There would be only one consistent set of laws, and it would happen to permit life. Others explore whether the constants could have varied over time or space in our own universe, though observations currently constrain such variations tightly. Still, others ask whether we have underestimated the range of conditions under which some form of life or complexity could arise, suggesting that carbon-based chemistry in liquid water is not the only conceivable pathway. Each of these ideas broadens the discussion, yet none has yet provided a complete and widely accepted resolution to why so many independent parameters align so precisely in our reality. One of the most striking and well-documented examples of fine-tuning that bridges nuclear physics and biology is the production of carbon inside stars. The element carbon, essential for organic chemistry, is forged through the triple alpha process in which 3 helium nuclei fuse. For this reaction to proceed at the observed rates, there must exist a specific excited state in the carbon-12 nucleus, the Hoyle state, whose energy level resonates precisely with the combined energy of 3 alpha particles. This resonance is tuned to within a fraction of a percent of the value that makes carbon production efficient. If the level were slightly higher or lower, the reaction rate plummet and the universe would contain far less carbon. The prediction of this state was made by astronomer Fred Hoyle before it was experimentally confirmed, and the precision of the match led Hoyle to remark that the universe looked as though a superintellect had been monkeying with the laws of physics. This remains one of the clearest instances in which fine-tuning appears to extend from the subatomic realm all the way to the chemistry required for life. The production of oxygen and other biologically relevant elements depends on similarly delicate nuclear resonances and reaction rates. The ratio of carbon to oxygen produced in stars is itself sensitive to small change in the strong force or electromagnetic coupling. Shift this ratio too far in either direction and the chemical pathways that led to water, organic molecules, and eventually self-replicating systems would be disrupted. Our universe sits in the narrow band where both carbon and oxygen are produced in sufficient quantities for the chemistry of life. This is another thread in the tapestry of coincidences that makes our existence possible. Even the familiar properties of water, often called the universal solvent, depend on the specific values of the fundamental constants. Water's high boiling and melting points, its ability to form hydrogen bonds, its anomalous density maximum that allows ice to float and insulate bodies of water, and its capacity to dissolve a wide range of substances all arises from the electromagnetic properties of hydrogen and oxygen atoms and the quantum mechanics of their interactions. Modest changes to the fine structure constant or particle masses could eliminate these properties or shrink the temperature range in which water remains liquid. While alternative solvents might support exotic biochemistries in other universes, the fine-tuning that makes water so uniquely suited to life on Earth adds yet another layer to this anthropic puzzle. The emergence of life also requires stable planetary environments over geological timescales, conditions that themselves depend on the tuning of gravity and electromagnetism. Gravity determines the size and densities of planets that can retain atmospheres and maintain internal heat for plate tectonics, which in turn recycles carbon and regulates climate over billions of years. Stronger gravity might produce planets too massive for stable surfaces or with crushing pressure. Weaker gravity might allow atmospheres to escape, leaving barren worlds. Electromagnetic interactions govern the chemistry of minerals and the cycles that keep a planet habitable. Thus, the fine-tuning reaches from the microscopic constants all the way to the macroscopic conditions that cradle life long enough for complexity to develop. As we consider these interconnected requirements, it becomes clear that the anthropic principle is not about a single lucky coincidence, but about a convergence of many independent conditions, each occupying a narrow window.
This deep unstructured
The
rumble.
joint probability of all these parameters aligning simultaneously by random selection is the product of their individual probabilities, resulting in a number so small that it challenges any simple chance explanation. Proponents of the multiverse argue that with enough trials, even the smallest probabilities are realized somewhere. Critics respond that without a mechanism to generate the trials and a rigorous way to define typicality, the explanation remains incomplete. This tension continues to drive research at the frontiers of theoretical physics and cosmology. The anthropic principle also invites us to reflect on the nature of scientific explanation. In most domains of physics, we see causal mechanism or deeper laws that determine why quantities have the value they do. For the fundamental constants, we currently have no such deeper law. They are inputs to our theories rather than outputs. The anthropic approach offers a different kind of explanation, one based on selection rather than direct causation. It tells us that the constants are what they are because other values would not permit physicists to exist and measure them. This reasoning is valid within its domain, yet it leaves many physicists dissatisfied because it does not provide the predictive power or mechanistic insight they seek. That satisfaction motivates the ongoing search for theories in which the constants emerge from the deeper principles or for empirical signatures of a multiverse that could render the selection principle testable. Visualizing what an untuned universe might look like helps sharpen the contrast. In a universe where the strong force is too weak for stable nuclei, there would be no atoms beyond hydrogen, no molecules, no chemistry, and no biology. Matter might remain a diffuse gas or plasma, never organizing into a hierarchical structures we take for granted. In a universe where gravity is too strong, the cosmos might expand briefly and then recollapse in a big crunch long before stars could shine for billions of years or life could evolve. Any complexity that arose would do so in a frantic rush, with no time for the slow accumulation of information that leads to minds. These alternative realities would not necessarily be empty of all phenomena, but they would lack the particular structures and long timescales that make our universe rich with possibility. The fact that we inhabit one of the rare corners of parameter space where complexity flourishes is what the anthropic principle forces us to confront. The principle also connects to other deep questions in cosmology and physics. The low entropy of the early universe, the extreme uniformity of the cosmic microwave background, and the flatness of space are additional conditions that appear tuned to allow the universe we observe. Inflationary cosmology was proposed in part to explain some of these features, yet many versions of inflation naturally lead to a multiverse, bringing us back to the same explanatory framework. The black hole information paradox and the nature of quantum gravity may ultimately shed light on whether the constants are truly free or fixed by deeper principles. Each frontier of research intersects with the fine-tuning question, suggesting that progress, one on front, may illuminate the others. Philosophically, the anthropic principle challenges our intuitions about chance, necessity, and meaning. If the weak anthropic principle and the multiverse are correct, then our universe is one of many and our existence, while precious to us, is an inevitable outcome in at least some regions of a larger reality. There is no special reasons for the constants beyond the fact they allow observers. This view can feel both humbling and liberating, stripping away illusions of cosmic centrality while still affirming the rarity and value of the conditions that make thought possible. If instead the fine-tuning point towards deeper necessity of intentional calibration, then the universe acquires a kind of directness. The emergence of complexity and consciousness may be woven into the fabric of reality rather than incidental to it. The principle itself does not decide between these interpretations. It simply makes the fine-tuning impossible to dismiss and demand that we think carefully about what it implies. As scientific tools improve, we may gain new leverage on these questions. Future measurements of the cosmic microwave background, large-scale structure, and the properties of dark energy may reveal whether the constants show variation or if they are fixed in ways that point to a unique underlying theory. Advances in string theory, loop quantum gravity, or emergent space-time paradigms could provide frameworks in which the parameters are derived rather than postulated. At the same time, the study of complex systems, information theory, and the origins of life may clarify how the fine-tuning at the particle level enables the high-level emergence of biology and mind. Each step forward refines the question without necessarily eliminating the mystery. Yet, even as knowledge grows, certain questions may remain at the boundary between physics and philosophy. Why does the universe contain not just matter and energy, but the capacity of organization, replication, and reflection? Why do the laws permit not only survival but the emergence of beings who can appreciate the elegance of the mathematics that describe their own origins? These questions do not yield to measurement alone. They require us to integrate our scientific understanding with deeper reflection on what it means to be observers in a cosmos that seems, at least at first glance, custom built for our existence. In the end, the Anthropic Principle returns us to the question with which we began, now deepened by everything we have explored. If the force of gravity were only slightly stronger or the nuclear force shifted by a single %, the universe would be a vastly different place, perhaps beautiful in its own way, but almost certainly devoid of the particular complexity that leads to stars, planets, chemistry, and consciousness. We would not be here to ask why. The fact that we are here asking suggests that our universe occupies an extraordinarily special region of possibility space. Whether this specialness arises from chance in a multiverse, from deeper necessity in a final theory, or from something more intentional, remains one of the great open questions of our time. The Anthropic Principle does not answer it, but it ensures that we cannot look at the night sky or the equations of physics without feeling the weight of that question. And perhaps persistent curiosity, that drive to understand why the universe allows us to exist and to wonder, is itself part of the fine-tuning we are trying to explain.